Okay, so last tutorial, 2.9. Okay, so question 1, fairly straightforward. You have a two-dimensional solid. You can think of it just as like 2n harmonic oscillators. And yeah, okay, so for part 1, part A, you want to obtain a formal expression for the heat capacity CV in terms of all the energies. So omega I indexes which of these harmonic oscillators. The I goes from 1 to 2n. Yep, okay, so for part A, you know the heat capacity is just given to you by the derivative of the average energy by temperature. So yeah, I'm pretty sure you can quote this formula all the time. And if you recall from the lecture notes on just simple harmonic oscillators, for a single harmonic oscillator, the average energy is given to you by that, what was it? H bar omega on 2 plus H bar omega divided by e to the beta H bar omega minus 1. So you have your vacuum energy or the ground state energy, depends on what field you're working in, and then you got all these thermal part. So if that represents a single harmonic oscillator's energy, for your entire ensemble of 2n of them, you can just treat this as summing up all 2n of these omega I. So you sub-index it by I. And this is I, and then you just basically summing over all of the I number of them, and you get the total heat capacity. So this whole thing is really just ddt of the summation of H bar omega I e to the beta H bar omega I minus 1 plus the ground state. Okay, so in this case, probably should write this as KT to make it clearer because you differentiate it with respect to temperature. But okay, so the second term basically drops out in this derivative. You don't have any temperature dependence. The first term, it's in the denominator, so it's a bit annoying. So you have to do like the chain rule, or the product rule a couple of times. But it's not that weird, and you should end up getting something like 1 over KT squared. Sum over I, you can take the derivative in and out of the derivative, no problems. H bar squared, omega I squared, e to the H bar omega I divided by KT, or divided by e to the H bar omega I divided by KT minus 1 squared. So you pick up all these random factors because of the chain rule that you have to do. But yeah, it's just a derivative, that one. And yeah, that's as far as you can go, like generally, because you don't know what these individual omega i's are, so you can't really simplify this summation any further. But that's fine. Like this is as far as you need to go for this question. So for part B is very closely related. It's just saying taking this expression, but evaluate it for Einstein's model. So for Einstein's model, it's basically assuming that all your omega i's are equal to the same sum omega. So every harmonic oscillator is the same, like kind of quantized energy level, and you can just get rid of this summation and get rid of all these sub indices. And just remember that because you're no longer summing over any explicit variables, you're just summing over 2n times. So I equals 1 to 2n. Then all you do is pick up a factor of 2n on the front because it's just summing over it. So CV is equal to just this expression, but without the weird sub-indexes. So 2n divided by KT squared, H bar squared, omega squared, e to the H bar omega on KT, divided by e to the H bar omega on KT minus 1 squared. And that's it. And that's really like all you have to do. Okay. So for part C, you have to then, in order to use the Debye approximation, one needs to find the density of state in 2 dimensions. So you need to find this sigma omega, which is density of state in terms of energy in 2D. And yeah, okay, so that's the first thing I have to do. So for density of state, it's basically, you can think of it in terms of energy, or you can think of it in terms of your wave vector k. Since they're related, it's pretty much the same thing. So, and because your density of state should be the same regardless of what like kind of basis you're working in. So if you have your density of state in terms of energy, integrating over energy, this should be the same constant number or like same number as if you had your density of state in k space and you integrate it over k. Because overall, these two are just like different bases that you're working in. Yep.
Question about this.
Yep.
When you look at the like how they do that density of state stuff in the textbook or whatever, for some reason you invent this eigen whatever k. But like, why don't we just use energy in it, and why don't we use k and change that energy one energy? This is the Schrodinger equation, right? Energy is already in there.
Why? Okay, let's see. I don't know if there's any physical reason. I think because most of the times okay, so in Schrodinger's equation, like for example, you get a lot of like derivatives, and they're really annoying to solve. So, but then if you go to Fourier space, then your derivative becomes just like, instead of saying like, say, d dx of a function of x, if you go to Fourier space, then it just becomes k times the Fourier function in Fourier space. So a multiplication is a lot easier to solve than a derivative. So it's usually like kind of convenient to do your calculation in k space. So then if you're going to be doing that, then knowing the density state in k space helps you like kind of not have to go back and forth. You don't have to keep Fourier transforming. You just have to Fourier transform once, do your solution, and then Fourier transform back once you have it. I think that's the reason. Like that's the reason I will motivate it. Yeah. Otherwise, yeah, like physically, there's nothing more natural about k space. In fact, yeah, like you said, energy is more physically intuitive. Okay, so the goal is to figure out this, and so indirectly, if we figure out this, then we can get that. This is a bit easier to figure out in this case, because if you, okay, this is kind of by definition. So this is the g of k is the degeneracy, and that's equal to the derivative of your density of space, density of states in k space. So this is actually your density of states in k space. I forgot the derivation for this, but you can find on Wikipedia that your density of states is related to the degeneracy this way. And so, okay, this one we can kind of like reason to find, because for the density of states in k space, you can imagine it to be, okay, this is pretty much defined as the number of spin directions or polarization multiplied by the total number of allowed states so this is total number of like k vectors that you can like physically like have in your system. So it depends on the energy. So if you imagine having some energy cutoff, then in your k space, kx, ky, you're going to have some like shell where like all the k vectors inside this area is allowed, but then ones outside are too high energy, and you with an energy cutoff that these are forbidden. So then the total number of allowed states represents the area of this kind of like allowed region. And because your maximum, you usually set some maximum energy, max energy, And the maximum energy corresponds to some like max length of K, of your vector K. So then if you have some maximum length allowed, so this is your K max, and you cut off everything around there, then it's the allowed region, this total number of allowed states is the area of circle of radius equal to this K max. Okay, and to make it a density, this is the total number of states. To make it a density, you divide it by the unit volume of states. Okay, since it's a harmonic oscillator, so you have 2 degrees of polarization, or like 2 degrees of freedom, and your total number of allowed states, area of circle, but since only positive K's are allowed, so this is actually area of a quarter circle. You only get the positive quadrant. So you get 1/4 of pi r squared, but r is your K maximum, so I'm just going to call it pi K squared. And then divide by the unit volume of the states. So this thing is a bit weird. You can think of this as if you have your physical box of length L, side length L, then inside you can fit standing waves, like when you solve your Schrodinger equation whatsoever. Then you get your condition, your boundary condition is going to be like, what is it? K equals like n pi on L or something like that. Yeah, like your boundary condition looks something like that. So your smallest K space increment that you can take, so this is like kind of increments up, like quantum mechanically, like quantized, and the smallest increment you can take is pi on L. So the smallest like kind of unit volume or the unit area, in this case is a 2D, is a small box in your K space with side length pi divided by L, which is the length of a physical box. This is the weird part. Like if you can get your head around this, I think you're fine. So it's just saying that you have some quantum mechanical increments, and the smallest increment is determined by your physical length. And so then, yeah, the larger your box, the smaller this gets, so you get a better resolution. If you have a very small box, this becomes a very large increment, so that you see the quantum mechanics effects more clearly. But yeah, so this is the unit volume that we're talking about. So you divide by pi divided by L squared, since it's 2D. So I should really call this unit area. Okay, so then simplifying this becomes 1/2, what's it? L squared on 2 pi K squared. And L squared, since our real box L, side length L squared is just the total area A. So this is also just A divided by 2 pi K squared. Okay, so all this effort is just to get this gamma K, which is the density of state. Then we move our way backwards to go back up and say, okay, with the density of states now found in terms of K, we can take the derivative to find the degeneracy. So then G of K is equal to A on pi times K, just differentiating that. And then now that we have G of K, we can then go back and find the density of states in energy. So we can then perform this integral. I need more space to do that. So I'll bring the other one down. Okay, so what we have so far is that G of K is equal to A on pi K. So to relate this back to sigma, so sigma omega d omega is equal to A over pi K dk. Okay, so now we can do a change of variable on this to turn it into an omega integral, because we know the dispersion relation. So the dispersion relation, if in this case, will just be omega is equal to the sound speed times by k. Is that the right way around? I always get this wrong way around. Yes, I got it the right way around. First go. Okay, so then k is then equal to omega on cs, and dk is equal to d omega on cs. So on the right hand side is just a divided by pi divided by cs squared omega d omega. Yep, so in this case you can, so then this is equal to sigma omega d omega. And okay, so now we technically have found sigma omega because that's just whatever's in front of here. So it's a divided by pi divided by sound speed squared times by the energy. But that's not the end of it, because once we've found the density of states, we then have to use it to find the cutoff frequency, the divide frequency, omega d. And yeah, remember that this cutoff frequency is defined as if you integrate your density of states up to this cutoff frequency, the omega, in the divide approximation, what you'll get is the number of normal modes. So the number of harmonic oscillators in your, the number of like equivalent harmonic oscillators in your system if you integrate up to here. And we know that for our system, we know we have 2n harmonic oscillators. So we've got 2n normal modes. So then we can then use this definition onto this expression to say integral of 0 to omega d, this divide cutoff frequency, a on pi cs squared omega d omega, this is then equal to 2n, because the right hand side integral, left hand side, same thing. And for the question to make it simpler, they told us that the sound speed is constant, so cs, this whole thing can come out the front. So at the end of the day, you just get a, let me see if I did this correct. Yes, I did. Okay, a on 2 pi cs squared omega d squared is equal to 2n. So there you go. You can invert this to get as omega as a subject. So omega d, the cutoff frequency is then 2 cs square root of pi n divided by a. So that's your cutoff frequency. Yeah. All good.
How do you get the pi over L earlier?
Oh, the pi over L is just what's it called? The quantization condition for your harmonic oscillator. So if you think about in K space, your Kx and Ky, you can't just take any K if it's a quantum mechanical system. So then you're going starting from 0, you have to go up in increments of pi divided by L, because your K has to equal to m pi L from your solution of the Schrodinger equation.
Right.
Yeah, so then you go up in increments of this pi L. So then you can think about saying that you can think of this like a resolution problem. Like the finest resolution you can have of your K space is this 1 cubic, not cubic, like a square cell side length pi divided by L. So then when we find the density of state, we then just think about the total number of allowed states and what's the density of that inside this little area. Like how many of them can we fit inside this little area? So that's like the density per unit area.
Right.
Yeah, so in 3D, you will have pi on L cubed in your expression. Yeah.
It doesn't seem like it worked very well. L is like small because like it's like a circle and then you're like all squares back on.
Right, yeah.
It's like a really small circle.
Yes, so as small, yeah, you're right. Like for very small L and your system is very small, then like your allowed states will look something like this. So then the positive quadrant approximation is pretty bad. Yeah, so yeah, it is something that's like only in a like limit of like a large number of states that it's like valid. But then in a small state like this, you can probably just count to the total number of states you're allowed. Yeah. Yeah, it's all good. Okay. Okay, so part D then. Okay, part D, using the Debye approximation, show that the heat capacity CV obeys this weird looking law. So saying that, show that CV looks like 2n times k. Wait, that's not the question. 2n times k, and then times some function of theta divided by temperature in 2D. So show that CV looks like that. Okay. So yeah, you're gonna have to kind of take a leap of faith here. So CV by definition in Debye approximation from the lecture notes is defined as k beta squared, 0 to the cutoff frequency, the density of state weighted by all your energies, so h bar omega squared e to the beta h bar omega divided by e to the beta h bar omega minus 1 squared d omega. So if you recognize that this is the CV that we got before, and they're kind of just integrating it over all the possible energies and weighted with some extra factors up front. But yeah, this is like exactly the same result that we got for part B. But anyway, okay, so that's the heat capacity. And now that we know what sigma D is, so just remind you that sigma D is equal to, I already forgot it, A on pi CS squared omega. So you can put that into here and just say, okay, then CV is equal to K beta squared A divided by CS squared pi integral 0 to omega D of all this rest of it. H bar omega squared e to the beta h bar omega omega d omega. Okay, so now we have to do is solve this integral, and the usual approach to solving these integrals is to define a dimensionless variable where you call x this whole beta h bar omega, just to declutter the whole thing, like just to make this doesn't look as scary as it should be. And okay, so once you're done, you have to also take that dx is equal to beta h bar d omega. So you're going to pick up some beta h bars from the d omega, and you're going to pick up some more beta h bars when you sub out the omegas from here. But then you know at least the exponent's going to be like neatly simplified. So then what you get after the substitution is k beta squared a on cs squared pi 1 over beta to the 4 h bar squared integral from 0 to beta h bar omega d e to the x cubed divided by e to the x minus 1 squared dx. So 2 powers of x come from here, 1 more from here, and then the rest of it's pretty standard. Okay. And now to get this into the form like that we want, we have to get rid of the A and then pick back out this N. And we remember that before when we got the omega D, we had the relationship that omega D is equal to 2CS square root of pi N on A. So we can write A as a function of N to put it back into here. So our A is actually equal to 4N times CS squared divided by omega D squared. So we can put this into here and eventually get out a term that looks like, so CV ends up looking like 2N times K, the N from the A over there, times by 2 divided by beta H bar omega D squared, 0 to beta H bar omega D e to the x cubed divided by e to the x minus 1 dx. Okay, so then if you compare this back to what we started off with, this whole thing back here, that's your F2D of theta divided by t. Except your theta divided by t is like implicitly defined in this betas and x's in there. Okay, cool. So that's part D. Now the last bit, part E. Part E says, okay, show that high temperatures and at low temperatures you get a bunch of results. Okay, I'll write that down. Let's put this on for now. So show at high T, at high T, you want to show that CV goes to 2nk. So your f of your function f2d goes to 1, and also show at low temperature, your CV goes approximately like t divided by some parameter theta to some power of alpha. So some exponent. So you want to show that it's linear at high temperature and it's follow some power law at low temperature. Okay, so let's do the high temperature first. So at high T, we can think of that as, okay, define this variable y is equal to theta divided by t. And at high T, when t is very high, this thing is extremely small. So it's a lot less than 1. So then if we write in terms of y, our f2d as a function of y instead of theta t, which is pretty much exactly the same as that one, except now you're calling something y instead of theta t. So that's equal to 2 divided by y squared, 0 to y of e to the x cubed, e to the x minus 1 dx. Literally nothing's changed. But now if we consider the fact that y is very small at high temperature limits, if y is very small, then that means this integral doesn't leave 0 very far. It goes from 0 to like maybe a little bit larger than 0, but like, you know, it's going to be a small increment. So what that means is that this whole integrand that you're evaluating is never going to get very large. So the x is never going to get to stray very far from 0. So you can approximate this by its Taylor expansion and truncate at a linear order. So you do a Taylor expansion of the integrand into the function in this case. So when you Taylor expand this, you get 2 on y squared, 0 to y, and e to the x becomes 1 plus x cubed, and you get the square here, 1 plus x minus 1 squared dx. So then this equals 2 on y squared, 0 to y, 1 plus x times x dx. Yes. Okay. So now if you take the limit of this thing where y goes to 0, then you realize this goes to 1, which is exactly what we want, because if this f of 2dy goes to 1 at y equals 0, then at high temperature, my CV is going to go towards 2 and k, because my f of 2d, in this case, this just goes to 1. Funnily enough, this exercise is a bit like semi-pointless, because if you never took the high temperature limit, and you never even bothered doing this Taylor expansion, and you just took the limit of y going to 0 for this general integral, you still get 1. So you don't actually have to do this. But then that makes sense, right? Because as y goes to 0, the behavior of this thing is the same as this thing. So it's not that surprising. It's just that, I don't know, sometimes it's intuitive to convince yourself this way, but other times, if you have a computer to work this out for you, you really don't need to take too many steps. Okay, so that's a high temperature limit done, and that's easy. So at low temperature, I'm just gonna rub this out because it's okay. At low temperature, then in this case, our y is very large, low T. So our f of 2d of y, which is 1 on y squared, or 2 on y squared, 0 to y, e to the x cubed, e to the x minus 1 squared dx. As temperature gets really low, then you can imagine that this upper integration limit goes to infinity. So it gets very high. So you can actually take it to infinity without like missing out on much. You're not gonna get it very wrong. And if you ever see an integral weighted by like a thermal distribution function in the denominator, and it has some e to the x times some power of x, this thing is going to be some Riemann zeta function of some order. So yeah, you can convince yourself of this by putting in Wolfram alpha if you want. But yeah, if you see an integral that looks like this, if it's x squared x to the 4, it's going to be some Riemann zeta function. In this case, is the Riemann zeta function of the third order. So it's equal to 2 on y squared 6 times zeta of 3. And zeta of 3 is approximately, this whole thing is approximately 7.2. So times by 2, this is about 14.42 divided by y squared. So that's our low temperature limit for this F2D. Then when we put back into a CV expression, then CV is equal to 2n times k times by 14.42, and then put back in the definition for y. So times by t divided by theta squared. So there we go. Our exponent alpha is 2. So that's all question 1. All good. And question 2. Okay, that was a hard one. The other 3 are fairly straightforward. Actually, I might have said the first one was straightforward too. Okay, question 2. What you want to do for question 2 is the fluctuation in the number of photons in the cavity mode R for a black body radiation in enclosure. It's given by sigma nr divided by nr. So sigma is the dispersion, or what's it called? Standard deviation, and divided by the number. So it's seeing how much does it vary given the amount of average number you have. And you're told that is given to you by something that looks like this. +1. 1/2. Okay, and you want to describe this behavior of this fluctuation, sigma nr, as a function of temperature. So describe sigma nr in terms of T. Okay, so to describe this again, we have to take a few separate limits. So let's take the high temperature limit first, high T limit. It doesn't matter what limit we're working at, the number density or the occupation number for this is going to be occupation number for photons. So you know it's going to follow a Bose-Einstein distribution. So it's going to be e to the beta h bar omega -1. And okay, that tells me that 1 over nr +1 is going to be inverse of this thing, +1, so the ones cancel out. So it's just going to be equal to e to the beta h bar omega r. And a high temperature, so T very much larger than 1, then beta h bar omega is going to be much less than 1. In fact, it goes to 0 at very high temperature. So the limit of T going to infinity of 1 over nr +1 is equal to e to the 0. So it's going to be equal to 1. So at very high temperature, sigma nr divided by nr is equal to 1. And what that tells you is that at high temperature, sigma nr is the same order as your occupation number, which is very large because at high temperature, you're going to have a high occupation number. And at high occupation number, your fluctuation ends up being the same order. That means you also have an extremely large fluctuation. Yeah, so you can describe it as saying that, yeah, sigma is the same order as nr at high temperature, which is extremely large. Okay, and the other limit is the low temperature limit. So low T limit. At low temperature, then you can think of as beta h bar omega is very large, with beta being inverse temperature. As T goes to 0, beta T omega goes to infinity. So in this case, the occupation number nr is approximately just e to the beta h bar omega, because you've overpowered this -1 term where it doesn't really matter. Comparing an extremely large exponential to a 1, you can just approximate just the exponential. So then 1 over nr +1 is again approximately e to 1 over e to the beta h bar omega. Wait, sorry, no, I got this wrong around. This thing is 1 over. So this is approximately e to the beta h bar omega. Yeah, so the occupation number is 1 over the exponential, then 1 over the occupation number is just the exponential. And again, we can ignore this 1 because we know this is going to be a huge number. Okay, so if we know this is a huge number, then basically this is it. So our expression for sigma nr divided by nr equals to 1 over nr +1 to the 1/2. But this entire thing inside is just approximately 1 over nr. So it's approximately 1 over square root of nr. Okay, so what does that tell you? So that tells you that sigma nr at low temperature is approximately equal to the square root of nr. So we take the nr to the right hand side, and now you have a square root instead of 1 over square root. So as t goes to 0, nr goes to 0, but your fluctuation goes to 0 slower than your occupation number. It goes down by a square root instead of linearly. So your fluctuation doesn't die down as fast as the occupation number. Yeah, and that's pretty much it. Okay. Question 3. Vin's law. Okay, so Vin's law, in the black body radiation, the energy range given is by something that looks like c t to the 4 x cubed e to the x minus 1 dx. And c is some really complicated constant that has like everything in it. Show that the distribution has a maximum at x at about 2.82. So there's pretty much no physics in this. You're just doing the derivative. You're just saying, okay, this thing is completely independent of x. So the only thing I have to like kind of differentiate is this function. So just take d dx of x cubed e to the x minus 1 and set that to 0 and find its maximum. Okay, so this is a slightly easier derivative than you have to do normally. So just 3x squared e to the x minus 1 minus x cubed e to the x minus 1 squared is equal to 0. Okay, and then you do some simplification, shove some stuff around, you end up getting 3 minus x is equal to 3 divided by e to the x. You can't solve that. I mean, you can't solve that by eyeballing it. You can either plot both of these lines and see where they intersect, or you can just put it into like, I don't know, Mathematica or Maple and just say solve for x, and then you end up getting x is approximately 2.82. Yeah, that's really all this first part is. The second part is asking, okay, how does omega change when T goes from 1000 Kelvin to 1200 Kelvin? So T1, T2 is asking how does omega change with the temperature change? Since you know the peak wavelength of your black body curve is going to shift. Oh, was that question? No, okay, sorry. So yeah, from high school, remember Vin's law. So your peak wavelength is given by the Vin's constant B divided by the temperature. Okay, and you know the wavelength can be related to frequency like that. So this thing is technically C divided by the peak frequency equals B on T. And your frequency is related to the wave number, the angular frequency omega by 2 pi. So then this just C, 2 pi C divided by omega peak is equal to B on T. So what that tells me is that the peak wave, angular frequency divided by temperature is given to you by some constant. This thing doesn't depend on temperature. So it doesn't matter which temperature I choose, they should equal each other. So then omega 1 divided by T1 is going to be equal to omega 2 divided by T2 at a different temperature. And now I want to find just omega 2 divided by omega 1 is equal to T2 divided by T1. And I put in T2 1200 Kelvin, 1000 Kelvin. So that's equal to 1.2. So that means as I increase the temperature by 200 Kelvin from 1000 Kelvin, my peak wavelength shifts by 20% towards a higher frequency range. Yeah. And that's it. So yeah, 20% increase. Okay, so the last one. Okay, question 4, specific heat due to spin. Okay, so you got some ferromagnetic solid and you're trying to look for the spin energy inside it. And the relevant information is that the dispersion relation could be written as omega is equal to some factor k times by q squared. Q is the same as k. Like what we've been calling k before, they're not calling q. Yeah, and we want to use this to obtain an expression giving the temperature dependence of the spin wave contribution to a low temperature specific heat of a solid. Okay, so we want to find a specific heat as a function of temperature. Find CV as a function of T. Okay, and okay, there's a lot of things that I didn't say in this question. So K is actually given to you as an expression. It might be in your textbook. 2 times J times the spin S times A squared divided by H bar. Yep. And your density of state is also given to you. Or you could like write this down. So you go V 4 pi Q squared divided by 2 pi cubed and Q d omega d omega. So this is kind of, it looks a bit weird, but it's exactly the same as how we derived it before for sigma. If you think about it, before we had sigma is equal to A divided by pi times by K squared. So the K is Q. Instead of area A, we now in 3D, we have a volume. And because it's a 3D, so then the area, the total number of allowed states, rather than being the area of a circle, is now the surface area of a sphere. So it's 4 pi r squared. And this 2 pi cubed is like a phase space factor. So for like n dimensions, you have 2 pi to the power of n factor into your density of states. And this is the Jacobian that we had before to get it back to d omega. So this is kind of thrown at you, but then if you look at it term by term, it makes exact sense on why it looks like that. But again, if it's given to you, then you can just use it like this. And given this relationship between omega and q, I can find this dq d omega. So this is actually simplified to v divided by 2 pi squared, omega to the 1/2 divided by 2k to the 3/2 d omega. Okay, and then from that, we can then find the energy. Once you find the average energy, you differentiate it with respect to temperature to find CV. So we need to find the energy first. So for energy, then it's really just going to be integrating with respect to the density of state over your distribution function. So V 4 pi squared H bar on K to the 3/2 0 to infinity omega 3/2 divided by e to the H bar beta omega minus 1 d omega. Okay, so where that came from is just your general expression for the average energy is just integrating over the density of state times by what's it? Your energy, h bar omega divided by e to the h bar omega minus 1 d omega. So it's just this general expression for integrating over your energy, but then putting the specific expression for rho of omega. Okay, so for in this case, the question specifically asks for low temperature limit. So at low T limit, this tells me that h bar omega is going to be larger than kT. So my energy is going to be larger than the thermal energy, which makes sense at low temperature. Okay, and then again, we change our variable from beta h bar omega to x. So again, do x is equal to beta h bar omega. And you end up changing this expression to look like E is equal to a lot of constants, so V divided by 4 pi squared h bar to the 3/2 k to the 3/2 beta to the 5/2 0 to infinity x to the 3/2 divided by e to the x minus 1 dx. Okay, so this one doesn't have an e to the x in the numerator, so it's not a Riemann zeta function. It's actually just, this whole thing is just approximately square root of pi. So, okay, yeah. Running out of room again. That's it. You get your energy down, and you have written it in terms of just constants and temperature. And you can just now differentiate that with respect to temperature to get the capacity. Yeah, so that integral, after writing it out properly, we get E, after solving the integral equals square root of pi, that's just equal to, E is just equal to V divided by 4 h bar 3/2 pi to the 3/2 k to the 3/2 beta to the 5/2, and then oh no, sorry, I don't want to write b. I want to write it in terms of explicitly t. So kt to the 5/2. All right, so instead of beta, just write kt. Okay, so now let's just take a derivative with respect to t for average E. It's just simple because it's just got one t there. You don't even have to do any weird chain rule. So just equal to 5/8 vk to the 5/2 divided by all the other junk. 3/2 pi to the 3/2 k to the 3/2 t to the 3/2. So there you go. You're saying your heat capacity as a function of t is proportional to t to the 3/2. So that's the relationship. And apparently they could get a fairly good experimental verification for that. And it was an important result in condensed matter physics. But yeah, like you realize that we're pretty much doing the same thing here over and over again. We're finding the average energy by integrating over all of the energies and taking different limits to make the integral doable. And then afterwards, once we found that, we take the derivative to find the heat capacity. It's the workflow is usually just pretty much going like that. Yeah, I think the only thing you have to really practice doing is recognizing some of the integrals, and also, yeah, knowing how to take these limits properly. But the rest of it is pretty much the same. And also, yeah, just try to intuitively understand what the density of state is talking about, because that's probably the only thing that requires you to have a bit of a leap. The rest of it is just math. Yeah, any questions? All good. Cool, okay, and this is it. Good luck with your assignment and exams, and yeah, see you guys around. No worries.